Welcome to my presentation of ZARM and the Bremen drop towers. Before I start my presentation, I will shortly introduce myself. My name is Merle and I'm working as Deputy Head of Science and Operation at the ZARM Drop Tower Operation and Service Company. I studied physics at the University of Bremen, and my journey at ZARM already started 2013. I did my PhD in physics at ZARM in the field of quantum optics, and I participated in over 250 drop tower experiments. So I can tell you firsthand that doing your research in microgravity is an exciting opportunity at the drop tower. I will start my presentation with a short introduction, then I will introduce you ZARM and the Bremen drop tower, as well as our new facility, the Gravitower Bremen Pro. Afterwards, I will give you a guide at hand about the requirements and the service provided if you're interested to do experiments in the drop tower. And in the end, I will give you a short overview about the research at ZARM, and I will end my talk with a short conclusion. Most of you probably heard of one of the most famous microgravity experiments where a hammer and a feather were dropped on the moon and reached the ground at the same time. And this is quite a beautiful demonstration of the universality of freefall, where different test masses fall with the same gravitational acceleration. And this principle goes back to experiments by Galileo Galilei, which, according to legend, were performed at the Leaning Tower of Pisa. And I'm showing you this example because here we can already identify two important microgravity characteristics, which is the microgravity time or freefall time and the microgravity quality, which is defined by the residual gravitational acceleration. And in the case of the Leaning Tower of Pisa, we have a microgravity time of around 3 seconds and a very low quality due to the remaining air drag, and we can overcome these obstacles with modern drop towers like our drop tower Bremen. Nowadays, there are a lot of other microgravity platforms like parabolic flights and sounding rockets, providing microgravity in the range of seconds to even minutes, or space platforms like the ISS or satellites, where the microgravity time ranges from several months to even years. And not only the microgravity time, but also the quality differs a lot. So scientists have to decide which platform suits their experimental needs best. And also the cost and availability and the hardware access needs to be taken into account. And the drop tower acts as kind of stepping stone for the other microgravity platforms and also into space. ZARM is located in Bremen, northwest Germany, and was founded in 1985. The most prominent facility is the Drop Tower Bremen, a microgravity lab which already operates since 1990. And over 9,000 drops and catapult launches were already performed, providing microgravity for over 300 projects from around the world. ZARM is divided into 3 parts. We have the Research Institute, which belongs to the University of Bremen. The ZARM Drop Tower Operation and Service Company provides the facility and the technical support. And the ZARM Technik is a spin-off, which is a supplier for attitude control and equipment for satellites. And next to the Drop Tower, we have at ZARM several more facilities. These facilities are mainly used for aerospace qualification. For example, we have a hypergravity lab equipped with a Centri 30G centrifuge, and the advantage here is that the mounting is compatible with the drop tower. So scientists can easily switch between the microgravity in the drop tower and hypergravity in the centrifuge. We have also a thermal vacuum lab and a vibration test center with a long stroke shaker. And now I want to explain to you the drop tower in a little bit more detail. So here you see a sketch of the drop tower with a height of 146 meters. The outer structure contains an inner tube which gets fully evacuated within 1.5 hours by 18 vacuum pumps until a final pressure of 0.1 millibar is reached. And this is done to reduce the air drag and to achieve a very high microgravity quality in the level of below 10 to minus 6 G. Since this needs to be done for every drop, the maximum number of drops per day is limited to 3 experimental ones. The capsules or the experiments are housed inside of drop capsules, and after the drop, the capsule gets decelerated in the 8-meter tall deceleration container filled with polystyrene pellets with an impact of up to 50 G. And in the basement of the building is the catapult system. For the drop tower, 2 operation modes can be used. With the drop mode, the capsule gets lifted up to the top of the tower and then released into microgravity, where the falling distance of 110 meters provides a microgravity time of 4.7 seconds. The second mode is the catapult mode, where the unique catapult system launches the capsule from the bottom of the tower onto a vertical parabola, and this enhances the microgravity time to 9.3 seconds. Here you see some impressions from inside our integration hall. And the experiments are integrated into a capsule structure, and placed around the capsule is a cylindrical case, and this is done to ensure that we have a pressure of 1 bar inside the capsule. Afterwards, the capsule is brought inside the drop tower. And here you see my colleagues from the engineering team preparing the drop capsule for the drop. Therefore, the cover of the capsule gets connected to a winch. And the winch, together with a slider, pulls then the capsule to the top of the tower. This is the deceleration container, and after the inner tube is sealed, the vacuum pumps start to generate the vacuum, and during the 1.5 hours, the scientists have access to their experiment via Wi-Fi from the control room. And when the final pressure is reached and the scientists have prepared their measurements, everything is ready to start the drop. As I already mentioned, the drop tower is equipped with a unique catapult system, which was developed by the engineer team of ZARM. And the catapult system is based on a pneumatic and hydraulic drive to accelerate the capsule with a maximum speed of 168 kilometers per hour within 260 milliseconds. And here you see the inside of the catapult chamber. After the launch, the deceleration chamber is moved below the vacuum tube so that the capsule lands safely on its way down. Now I want to present you our new facility, the Gravitower Bremen Pro. And this is a new type of a drop tower, which is based on a guided approach, which does not require any vacuum. And therefore, the experiments are housed inside of sliders, which gets then accelerated via a rope drive based on a hydraulic winch. And the complete Gravitower is built inside the integration hall, so the height is limited to 16 meters. Due to the acceleration on the vertical parabola, some vibrations from the drive might couple into the experiments, and this needs to be prevented. Therefore, we have developed a novel release caging mechanism to decouple the experiment from the slider. So the slider acts as an air shield, and as a result, no vacuum is needed. But we can still reach, with this concept, a very high microgravity quality of 10 to minus 4 G. And another big advantage is that the repetition rate is much higher than in the larger drop tower with 960 runs per day. And another quiet feature of the Gravitower is that the flight parabola can be fully customized according to the needs of the experiments. If you want to use the maximum microgravity time of 2.5 seconds, you have to use also the maximum acceleration of 4G. But if your experiment is a little bit more prone to the hypergravity phase, you might want to choose a softer acceleration of 2G, which still provides a microgravity time of 1.9 seconds. And on the right-hand side, you see the flight parabola in red, and in blue, the acceleration with the initial acceleration in the beginning, the microgravity phase in the middle, and then the deceleration in the end of the flight parabola. Again, I want to present you some videos or images of the gravity tower. As I mentioned, the gravity tower is built inside the integration hall, right next to the large drop tower. And the scientists have access to a user interface to customize the flight parabola, where they can change the initial acceleration and deceleration, as well as optimizing the transition into microgravity with an additional smoothing function. Due to the low initial acceleration, combined with the decoupling of the experiment from the slider, we can have a very smooth transition into microgravity, which can be seen here in this demonstration video. The scientists have easy access to their experiment. It just takes a few seconds to just stand up, open the doors of the gravity tower, and then rotate your experiment to, for example, exchange some probes or do some adjustment to your setup. Here you see some images of the rope drive and the hydraulic winch. And another nice feature of the gravity tower is that it's fully compatible with the large drop tower. So if needed, you can do some experiments in the gravity tower in the morning, and then we just take out your experiment, integrate it into the capsule, and use the same capsule for example, a catapult flight in the afternoon. For the future, we're planning to update the gravity tower so that we have 2 additional operation modes. The first is partial gravity, like the gravitational acceleration of Moon and Mars, for example, and this gets more and more important in the field of human exploration and technical development. And the second operation mode is the so-called G-vectoring, where the gravitational acceleration is changed during the flight phase. Hopefully you are now interested in doing also some experiments in the drop tower, and therefore I want to explain to you some of our requirements and constraints. And the most important constraint is or concerns the size and the mass of your experimental payload. We provide 2 different capsule sizes, so the standard capsule, which is a little bit smaller, and a larger version of it if your payload has a larger height. And the longer version of the capsule can only be used in the drop mode, while with the standard version you have the free choice between the drop, the catapult, and the gravity tower. For both cases, the maximum payload width is the same, and also the maximum point load of 50 kilogram. But what differs between the operation mode is the maximum payload mass, which is, for example, for the catapult 165 kilograms. But you don't have to worry. We will help you with any question and some advices so that you can prepare your experiments to match the requirements of the drop tower. And of course, your setup also must be designed to withstand the impact of 50G. And this might sound quite demanding, but with a proper mounting and a stable construction of your experiment, this is achievable. And for example, the experiment I was working on even contained a custom-built laser system where we didn't even have to adjust the laser system between the drops. Every capsule contains a capsule control system equipped with or used for the experiment control and triggering, as well as the data acquisition. And the lower platform contains a power supply via batteries, providing 24 volts. And also the condition inside the capsule can be changed according to your needs, but this is only possible for the drop and catapult mode. As I said, the pressure needs to be constant at 1 bar inside the capsule, but we have vent lines available if you require vacuum or gases. And also the temperature can be changed with heating and cooling circuits. During your drop campaign, you have a team of engineers by your side from ZARM, which will help you with every problem and support you during your stay at ZARM. And they are also responsible for the mechanical and electrical integration of the experiment into the capsule, as well as the LabVIEW software interface for the data acquisition. And they will also support you with the experiment control, with the standard network connection, where we provide Wi-Fi and TrueLiFi. And we at ZARM also provide some equipment, for example, 2 high-speed camera systems with necessary lenses and illumination, if you need non-standard power supply or different vacuum pumps. And I will highly recommend you to have a look in our payload users guide, which you can find on the ZARM website. In the end, I want to give you a short overview about the research in the drop tower. And the drop tower is mainly used for scientific experiments in various research fields, ranging from combustion to fundamental physics to fluid dynamics and planet formation, as well as material science, and also experiments from the field of biology and chemistry. At ZARM, also some hardware tests were performed. For example, the microscope satellite mission, as well as the Hayabusa mission, tested their payloads in our drop towers. And most interesting for you might be that ZARM also participates in some student programs. We have the drop test program, REXUS, BEXUS program, and of course the Petri program. Thanks to the good partnership with ESA, ZARM has already been involved to the Petri program since 2009. And we are happy that already 18 students' teams were selected so far, doing their experiments quite successfully in the fields of science and technology developing. And hopefully your experiment ideas add up to the exciting science in the drop tower. And with this, I come already to the conclusion. So the Bremen drop towers are microgravity labs for research and technology tests and act as a stepping stone into space. The drop tower provides a microgravity time of 9.3 seconds with a very high microgravity quality and 3 experiments per day. On the other hand, the Gravitower Bremen Pro provides 2.5 seconds in weightlessness with a high repetition number of 960 experiments per day, and hopefully in the future also a partial gravity option. And with these take-home messages, I'd like to thank you for your attention and hopefully meet at ZARM.
Hello out there, my name is Hilde Stenuit. I'm a plasma astrophysicist from education, and after that I started working with the company Space Application Services. I'll tell a bit more about the company later on, and I did a number of different functions, among which supporting the European Space Agency in a function of Mission Science Office. And now since a couple of years I am supporting our commercial service called IceCube's International Commercial Experiment Cube Service, and we have a facility on the International Space Station, and that's what I want to tell you a bit more about. First question is, why would you think of some ideas of going to space, and in particular, why would you think of the International Space Station? So first of all, space is a very interesting environment, and in particular also the International Space Station, for different types of research. And the reason is that in the space station there is microgravity. So that means the space station is in a constant state of free fall with everything that is in it. It falls over and around the Earth with the astronauts, with every biological organism, every material, every fluid that is in the space station. It falls and it falls and it falls, and so everything floats. And that is actually very interesting to research. People have been doing that since more than 2 decades, and they have found interesting effects of the fact that we have reduced gravity, both for the life sciences, and on the slides on the left you see some interesting effects or benefits of doing microgravity research on the life sciences, like for cells when you do cell biology, or when you make crystals out of proteins, for example. But also for the more physical sciences, there's interesting effects. So you don't have sedimentation. So sedimentation means that everything that is heavier goes downward here on Earth. You don't need to deal with that when you are on the space station. No sedimentation, no convection. And so you can create interesting homogeneous spherical shapes, for example, more symmetric growth of different materials, of different fluids. So these things are very interesting to look at from a research perspective. Another aspect is radiation. On the space station, the distance from Earth to the space station is actually closer than the distance from Brussels to Berlin. But still, it's interesting to also investigate radiation because it's about tenfold as here on Earth. And so also that for research purposes, it's actually very interesting. People also use the International Space Station and space in general as a kind of test bed to test technologies, to demonstrate technologies, to validate technologies as well that they may want to use later on in satellites, in spacecraft. And they may want to test systems or subsystems to raise what is called the technology readiness level, the TRL, or to look at proof of concept or de-risk some of these concepts or technologies. So it's another category that you can use the space station for, is to demonstrate or validate technologies. And third, more and more, we see another category of research and development that goes more towards applications, industrial applications, even for sectors that never thought that they would have anything to do with space. So we see more activities also in applied research that relate to sectors like food, agriculture, biotech, even cosmetics or materials and manufacturing. So that's also interesting to think about, like, can we go more in the direction of applied research and development? Now, the International Space Station as a platform, so you may wonder why this platform is interesting to do this type of activities of research or technology on the International Space Station. So if you compare the International Space Station with other microgravity platforms, and specifically on the aspect of microgravity, you see that on the one hand, when you compare, for example, to parabolic flight or drop tower, also to sounding rockets, that obviously the exposure time of microgravity that you can study or that you can have your investigation run in is much longer. So the space station, you can actually have microgravity for days, for months, even for years, if you would like that. To look at microgravity and also radiation aspects. The other, and you see that on the chart, is a microgravity level. The microgravity level on the space station is actually good in the sense that it's far reduced, so it's done around 10 to the minus 5, where on other platforms that might be, for example, on parabolic flight, it might be more around 10 to the minus 2. So in the sense of microgravity, the International Space Station is a very interesting platform, both for the length of exposure as well as for the level of microgravity. So I mentioned that people study and use the International Space Station for studies on microgravity, on radiation. There's other aspects why the International Space Station is interesting. One is that it's in space, so it's surrounded by the extreme environment of space and of vacuum. But also people use it for its vantage point, so the view that you can have from either space or from Earth, from the International Space Station, is also very interesting. Now, I will be talking about the platform IceCubes that is on the inside of the space station. So we will be mostly dealing with research related to microgravity and radiation, or with technology validation. There's some other characteristics on here from the International Space Station: the speed at which it flies, where it is in terms of height, and the orbit specifics, and also how long crew members typically stay and how many of them there are, because they are, of course, also an interesting object of study. So about the IceCube service, or the IceCubes platform. So I'll tell a bit more about our service and who we are and what we do. So IceCube stands for International Commercial Experiment Cube Service. So it's international, that's obvious. From any nation, entities can actually access the space station through the service. It's commercial. We have set it up in such a way to make access fast track and direct. So we can fly modules actually to the space station in a very fast track way. And these different modules, and I'll tell a bit more about these cubes or modules, they can contain very different mission content. So in the sense of research or technologies, as I mentioned before. One thing that we specifically address with the service and where we can help also is what we call spatialization, is like how can you make your technical setup in such a way that it works in space. IceCube service has been set up by our company called Space Application Services. It's a Belgian company. The company was founded in 1987, initially mainly on human spaceflight, but then expanded and also in directions of the activities. The company also has a subsidiary in the US, in Houston, and we have people working in the Netherlands, in Germany, and you see some of the locations on the bottom of the slide. The service has been set up in a partnership with the European Space Agency, and so what we mainly fly are these cubes or modules. We set up the service in such a way that it's modular, so that it allows for these different modules or cubes that are meant as plug and play. So you plug them in and you can run your experiment. You have the possibility to build actually these cubes with what is called commercial off-the-shelf components, so components that you can buy in a shop that are available commercially. And so you can relatively easily build up your own setup inside these cubes or modules. They are meant to be installed very easily, so they have a common interface connector that goes into the facility, and once they're installed, they can run whatever they want to have inside for research or technology. As automated as it can be, so typically the modules have a protocol that is run in an automated fashion. I mentioned the volume of the facility. That is the total volume inside the facility, but typically we fill it with different modules at one single time. So you don't need to take up the full volume, obviously. We can actually have different models of cubes or modules. Some will be installed in the facility, like you see on the slide on the left, so they will be plugged into the facility. But we can also have some that are wired, like the one on the right. So we have also on the front of our facility, and that's then in the module where the astronauts are, we can also wire one of the cubes actually on the front. So that cube can actually be in the aisle, as it's called, in the module of the space station where our facility is based. In addition, we can also have cubes that are wireless. So they communicate with the facility through the wireless, and that allows for other technologies, like, for example, docking subsystems to be tested in the module. And also we can have the crew interact with some, as in particular the cube on the right that is in the module. The crew can actually interact with that module easily if that is wanted for whatever is done inside that cube. We talk about ice cubes, so you would think it needs to be cubes. Well, that's not entirely true. So we try to work with standardized plug-and-play modules, and they typically start from what is called a 1U, that is 10 by 10 by 10 centimeters. But in fact, they can have very different sizes, so you can have double, or you can have 2 by 2U, so 20 by 20 by 10. But it doesn't even need to be cubes. In fact, we had a greenhouse. You'll see a picture later. That was a cylinder. You could have an L shape. Everything's possible. Also, in terms of sizes, we typically talk about these U's as a unit, 10 by 10 by 10. But if yours is 1.5 U, so 15 centimeters long, that obviously also fits. So all of that is possible. And you can see we can fill the upper layer. So that's basically 4 by 3 locations or slots. and also underneath what we call the framework, so what is in the middle, we can have on each side 4 of these 1U. So in total, we can accommodate 20 1U boxes or modules at one time. In the scope of the battery program, the ESA Academy prefers that you use up to 2U for your module that you can come up with ideas for. It can obviously be smaller, but it would be assessed on a case-by-case basis, and in general, 2U is the limit, let's say, for those battery projects. In terms of characteristics of the facility, I put here some numbers, what you can expect in terms of power. So there's 5 volt, 12 volt, and up to around 40.5 watts per cube location. In terms of the data, so the data downlink is up to 4 megabits per second and uplink up to 0.5 megabits per second. For sure, you don't need to remember all of those numbers. In fact, at the bottom, I put a link to the more technical documentation if you want to dig and while you are doing your ideation. All of these cubes or modules use the same interface connector. So that's crucial, that whether you have a cube, a cylinder, or another form, at least the interface connector need to be the standard interface connector that is used on the facility. We use forced air ventilation in thermal sense, and the communication is through standard internet protocols. What is very nice, I think, is that you can have unique real-time interaction capability. So in fact, you can send commands and get data from wherever you like directly to your module while it is installed in the facility. So you can adapt your parameters, you can change software if you would like, and you can change the protocol if that's something that you would like to do for your idea. In terms of the general process, so our team is helping also the ESA Academy in the design and the development phase, also for the testing and the certification. And then the exciting moment would come that your module could be launched to the International Space Station. It would then be installed by the crew into the facility, and there would be operations support in such a way that, as I mentioned, you can send commands or get your data immediately from your module to your university or your lab or wherever you like it. So there is this real-time connection. When your experiment is finished, the crew will remove it from the facility, and if that's desired or required, the experiment can be returned. That's not something that is standard included. Some experiments actually can have all the data coming down through what is called downlink. They don't need to return the cube, but it is a possibility if it is required for sample analysis, for example. And so in terms of typical mission profile, I put here a profile for an experiment with samples, maybe biological type of samples that would be prepared, could be in your lab, and they are shipped to the launch site. Here I took a mission profile with a launch on a SpaceX vehicle. So they would be integrated at the launch site, for example, and installed on the launcher with late access if that is needed, for example, for biological samples that might not be needed if you're looking more at technology, for example. The launcher would bring it to the space station. It would be installed. There would be the protocol removed, and SpaceX or another vehicle could return it. Samples would be retrieved, if that is the case for your experiment, could be retrieved in the US, and the samples could be shipped, or the whole setup could be shipped to Europe. Or, as mentioned, you could analyze the data if they are coming down through the data downlink. So a couple of examples of cubes that we have flown in the past, just to give you some ideas of the type of modules or cubes that we deal with. So I put some here on the chart, but I will not talk through all of them. But on the left, you see the greenhouse I was mentioning, so the cylindrical greenhouse, not a cubic greenhouse. And there's also some interesting research done on biomining. We have an incubator for crystallization of proteins and large molecules that we fly on a regular basis with a Japanese partner. And there's some other more technology related, like the validation of a spectrometer or cybersecurity related. More examples related to genetics, related to microbiology on banana disease or fluid physics, or more related to coding. And the one on the right is actually another example of a university, a team that has actually won the competition in one of the previous years, and they tested a diamond magnetometer. Some more examples of what I think are very nice stories and research that we have done in the facility. So there was the first COVID drug research in space through this protein crystallization service. We also did some research related to cellular meat, for example, with cow cells and how these cells proliferate in space, or a genetic study on human skin microbiome of diabetes patients, just to give some examples. There's another chart with more examples, but I put the links to our website, so if you want to glance over, and it might give you additional ideas of what type of research can fit in those cubes or modules. And then last, I wanted to mention a couple of assets that we have actually integrated with the facility on board of the space station that are there also for you to use. So we have on board artificial intelligence capability in what we call the AI box. So it's there for users to actually access it and make use of it for any AI that is either previously trained on the ground, or for AI models that can be trained directly on board. And so you can actually use this or test AI as part of this AI cube, or you can actually connect it with your cube or module that you install in the facility, and you can actually have real-time processing based on AI with return to your module if that can be useful for your idea. And similarly, we also have a media set that is connected to the facility. So you can think of this as a webcam that allows also for interaction with the crew, with the astronauts, and also that might come in handy for any of your ideas that you can think of that might be using the facility and where it might be interesting to interact with the crew. You could also think of applications like health applications that are based on camera of the face of astronauts linked to AI, for example, and combine the media set usage with the artificial intelligence box with maybe a module or a cube that you're thinking of. And I think that describes why I think the International Space Station could be an interesting and relevant platform, maybe for your ideas, and that our facility of the IceCube service is also there and available for you if you come up with some ideas in the context of battery. Good luck.
I'm going to present you a parabolic flight activity with an Airbus flying in the sky, the A310 0G. My name is Frédéric. I'm in charge of a scientific parabolic flight for Novespace, a French company located in the southwest of France in Bordeaux. We are doing parabolic flights since 1989. We are a company, a subsidiary from the French space agency, the CNES, and we are working for various space agencies in Europe. So ESA, European Space Agency, of course, and the German space agency, DLR. We are doing 6 to 7 campaigns a year and more than 30 flights per year. Novespace is the owner and the operator of the A310 Airbus 0G. We are mainly doing a parabolic flight campaign for science. We are boarding some experiments, and this is more than 85% of our activity. We have performed so far more than 20,000 parabolas. A parabolic flight is starting with this A310 aircraft in 2015. The aircraft has been qualified by Airbus Industry and, of course, authorized for the flight by the European aviation authorities. This is the A310 in flight. with Patrouille de France, airjet from the Minister of Defense in France, flying close by our Airbus. And as you will see, the aircraft is going to perform a parabolic flight maneuver. So at the beginning, the aircraft is climbing quite high, reaching an angle of 50 degrees in the sky. And then pilot inside are maneuvering and making a kind of parabolas maneuver in the sky just to create 0G. So before to operate the S310 0G, we have performed since 1989 parabolas with older aircraft. We started with a Caravelle and then with the S300, which has been operated until 2014. Inside the aircraft, this is the biggest volume dedicated for parabolic flight for science in the world. You can see the cabin. It is a 20-meter length and 5-meter width. Here you can see some experiments installed inside the aircraft. We can board up to 12 to 15 experiments and up to 40 scientists. Here are the dimensions of the cabin. So inside the cabin, the pressure of the cabin is different on the ground. While on the ground you are at 1 atmosphere, inside the aircraft it is 825 millibars. The temperature is regulated between 17 to 20 degrees. The cabin humidity is quite low, it is just 15%. And the noise level can reach up to 88 decibel. We provide, of course, electrical power for the scientists, for the experiment to operate. We got up to 10 electrical panels on board. We only provide 230 volt AC. We also provide a connection to the outside. This is what we call a venting system. So we can connect some chamber to make a vacuum or to exhaust some product outside. This system is directly connected to the outside, so the pressure is directly related to the altitude of the aircraft. As you can see on the slide, we can perform different levels of gravity. We are mainly doing microgravity, so 0G parabolas, and the parabolas lasting around 21 seconds, but we can also do lunar and Martian G. In fact, we can do any level of gravity between 1 and 0G. You can see on the slide the quality of the parabola. In blue, you've got the vertical acceleration, what we call the 0G acceleration. As you can see, this is quite stable during the parabolas. As you can see, the acceleration is not completely stable. Experiments are selected 10 to 9 months before the first flight. A Novespace engineer will be appointed for your experiments. He will come and visit your experiment in your lab, and then it will support your experiment through the various safety process. 1 week before the flight, we will have a preparation week. You will arrive with your hardware, you will prepare your hardware on ground, we will review your hardware, and then we'll board it. And we will get a final safety review before the flight. Then during the flight week, we will have 3 flights over 3 days. Each flight is made with 31 parabolas. So as you can see, here is a parabola. The aircraft is flying at cruise level, and then we will increase the altitude of the aircraft. We will climb up to an angle of 50 degrees. During that period of 20 seconds around, everything inside the aircraft will weigh roughly twice its own weight on ground. So we will reach up to 1.8 G. Reaching 50 degrees angle, then the pilot will pull on the stick and we'll start this maneuver parabolic flight where we will be in weightlessness. So for 0G parabolas, it will last around 20 to 22 seconds. While we reach a negative angle of 42 degrees, then the pilot will pull on the stick to go back on the flight cruise level. Then during that period of also 20 seconds, we will support 1.8 G. In the cabin, there will be some announcement through the public address. 1 minute before the parabolas, there will be an announcement, 1 minute parabola number, and then you will get the announcement 30 seconds, 20, 5, 3, 2, 1, and then pull up. Pull up means that we leave the flight cruise level and we start to climb. So we are entering the hypergravity phase. During that period, there will be some announcements, 30, 40, meaning 30 degree, 40 degree. This is the angle of the aircraft. And then reaching 50 degrees, there will be an announcement injection, meaning we leave the hypergravity phase and we are entering the microgravity phase. During the microgravity phase, there will be an enhancement at the end of the parabola, 20, 30, meaning minus 20 degrees, minus 30 degrees. This is the angle of the aircraft. And while reaching 42 degrees, then there will be pull-out enhancement, meaning we are leaving the microgravity phase and then we are entering the hypergravity phase. So this period is lasting around 20 seconds again, and then we are back to cruise level, ready for the next parabola. So here is some recommendation for preparing your experiment. The first one, which is really the most important, is read the documentation. We've got a huge technical documentation which will help you to design your experiment. My second recommendation, take care about the procurement process. Ordering equipment could take some time and you have to take it into account in your process. Be sure your experiment is ready in advance. I strongly recommend that the design of your experiment is completely clear 4 to 3 months before the campaign. Fourth recommendation, please try to limit as much as possible the operation during the flight and especially avoid operation during hypergravity phases. And try to limit the number of tasks to be done during the 0G. Fifth recommendation, be compliant with the requirement. If you are not compliant, then it means no flight for you. Additional requirement for you. If you have a medical experiment involving human test subject, be sure that your experiment is endorsed by a medical doctor. We will ask you to have an approval from ethical committee. If your experiment involves some product and materials involving some hazards, be sure to use the safest product as possible. General recommendation, try to use commercial on-the-shelf equipment. Try to avoid to design everything on your experiments. If you have any products, liquids, powder, try to think to put everything inside a double containment. Last recommendation may be the most important. Listen to the recommendation from the Novespace engineers. Okay, it was a general introduction to the parabolic flight, and I hope to see you soon on board with your own experiment.
Hello everyone, I am Martí Vilella, and I am the manager of the Orbital Robotics and GNC lab at ESA Tech.
Hi, my name is Willem Suter, and I'm a young graduate trainee at ESA for the Automation Robotics section.
With our team, we take care of the test facility for Orbital Robotics, which consists of a flat floor where we are able to test equipment from industrial partners and other research entities in the matter of any weightlessness operations in space. I am the lab manager, as introduced, and Willem Suter is a young graduate trainee in space robotics, and he is the principal engineer for the REXUS platform, which is one of the main platforms that we have in the lab. In the Orbital Robotics lab, we have multiple focus areas. These focus on orbital satellite servicing, on-orbit construction, debris removal, and any other sort of low-gravity experiments that can benefit from a weightless interaction with the floor. The largest facility we have in the lab is the Orbit facility. Orbit stands for Orbital Robotics Bench for Integrated Technology. And it is an extremely flat floor. It's the flattest in Europe that allows us to simulate 3 degrees of freedom for any robotic systems on it. This way, you can simulate the weightlessness of space, even if it's on a restricted set of degrees of freedom. We accomplish this by leveraging the principle of air bearings. Air bearings are effectively just a layer of air that is projected onto the floor, like you also have the air hockey tables on cinema halls. And this makes a gap of 5 to 10 micrometers that allows us to have no friction with the ground whatsoever. We have developed many test campaigns in the past, ranging from everything from Spacewalk, which is a legged rover that can hop around the moon, to other systems that are just meant to be in orbit and interact with each other. In this video, you can see how Spacewalk is able to jump around the different sides of the orbit facility while engineers keep moving the platforms to support its jumps. We also have REXUS. This is our heaviest floating platform. It consists of 8 air thrusters and 1 reaction wheel that allows us to simulate how a satellite would be steering itself while in orbit. REXUS is able to move around in space with a very high precision And then it's also tracked with a set of cameras that we have around the lab to always be able to tell very accurately where it is in space. The Orbit flat floor facility is an extremely flat floor that has a flatness of less than 1 millimeter. Between the highest peak to the lowest valley, there is less than 1 millimeter. The floor itself is 5 by 9 meters large, and it has a very small inclination for which any tests are effectively floating. The whole lab is supported by the Vicon motion capture system. This is the same system that the cinema industry uses to be able to film any actors and project them into a CGI setting. Just like the cinema industry, we're able to leverage this in order to tell where everything is in the floor and across the whole workspace of the lab very accurately. We have a precision of sub-millimeter and a refresh rate of 250 Hz. Together with the installation around the Orbit facility, we're able to create a repeatable origin reference frame for which all experiments can be based on. In order to support the different activities that we do in the lab, we have an experienced group of engineers that are able to take care of everything from filling the air tanks of our autonomous floating platforms to lifting them between the floor and the ground where they can be maintained, as well as operating KUKA robotic arms to support any interactive scenarios in the flat floor facility and interacting with our existing floating platforms like REXUS. We also have Mantis. Mantis is a passively floating platform that has a payload capacity which is slower than REXUS. Mantis can only support 35 kilograms of payload on top of it, but this still enables us to have multi-body interaction in the flat floor facility. All in all, both platforms can have autonomous operations without any tethers to limit the interaction with outside environment, and Mantis specifically supports 15 minutes of autonomous operations.
Coming back to REXUS, the main platform we use on the Orbit facility. REXUS is made up of 3 stacks. The first stack, Recap, contains the reaction wheel, which allows us to control the orientation of REXUS. Underneath, you have SatSim, the satellite simulator. It contains 8 compressed air thrusters that allow us to control both position and orientation of REXUS through discrete firing of those thrusters. Finally, on the bottom, we have Acrobat, the air cushion robotic platform. This is the platform that generates the air cushion between platform and ground and therefore removes the friction, allowing REXUS to move freely on the Orbit facility. It also holds our onboard computer and the hardware interfacing electronics for the rest of the stack. When put all together, it forms REXUS. REXUS has a total weight of 200 kilos and can therefore sustain 50 kilos of payload. It has a centered center of gravity, and when tethered, has an infinite amount of time of autonomy. However, when on its own, can survive 25 minutes as a free-floating platform, or roughly between 15 and 5 minutes when being controlled. To control REXUS, we have developed REXUS Control. This is a software architecture based on ROS2 packages. As an input, we have a gamepad controller, which allows us to generate trajectories to be followed and to actuate the thrusters or the reaction wheel directly from the gamepad. The Vicon system is also linked to our software architecture and therefore allows us to visualize or get live tracking information directly and in real time. To make the interaction with the hardware easy, we have already developed drivers such that we can send directly commands to these different actuators and that they can be integrated in a closed loop with the REXUS control. We also have a live visualization based on RViz that allows us to see where the platform is, how it is being actuated, and see its position with respect to the unevenness of the flat floor. We've also developed a simulator to test your REXUS control packages prior to being tested on the flat floor. And we've done so in an easy plug-and-play fashion that allows you to develop, test, and validate solutions prior to coming and testing it on the actual physical hardware.
So now that we have introduced our facilities, we want to talk about the educational projects that we can do with them. We are able to support everything ranging from using your own payloads in our floating platforms to using our existing platforms to develop control algorithms and other software solutions for them. Our main focus point is REXUS. REXUS is our big satellite simulator. It currently has some controllers that leverage MPC control and nonlinear control. However, this can always be improved. This is a platform with a lot of actuators. It has 8 air thrusters and 1 reaction wheel, so the opportunities of controlling this in different ways are limitless. You can do everything from tuning our existing controller and performing system identification on the platform to achieve better control, as well as developing an entirely new controller, testing it with our existing software stack and simulator, and ultimately integrating it with our physical hardware and being able to test it in the lab with us. Besides this, you can also do contact dynamics research. We're able to support this with the presented REXUS platform, as well as Mantis, our smaller floating platform, and even the Cooker robotic arm. All of these different systems can interact together so that you're able to touch different bodies and this way be able to develop technologies that in the future could be flying to orbit. Other things that you can do is really anything you want. We are available for you. We have support for your payloads. Anything that has to do with floating, we can support. And we are always keeping an open ear for any innovative proposals that you would like to follow up with us with. But while we are able to do a lot, you must keep some things in mind. There are some things you must be looking out for. You must understand that the software we use is all based on ROS framework. We use ROS2 Humble. This is the very latest at this moment. And through this, you are able to have pretty plug-and-play interaction with our existing floating platform. By the fact that we're using ROS, this means that you must be developing in C++ or Python should you wish to use our existing software solutions. We have provided a manual that specifies how any payload can be attached to our platforms. You must adhere to the mounting instructions and the payload limits, as well as making sure that there are no loose objects floating in the floor. This floor is very delicate and it is precious. There cannot be any items ejected onto it. If you're using equipment that has moving parts, this can lead to a change in inertia. This change in inertia could mean that the momentum of the platform when it's moving around is influenced. So you should try to limit that. Besides that, keep in mind the maximum payload limits. For REXUS, this is 50 kilograms, and for Mantis, this is 35. If you use any external sensors, don't forget to synchronize your data. You will find out the hard way how it is very hard to synchronize data from different input sources on the get-go. Think of a solution before coming to us. And lastly, if you're developing a new controller or using our existing controllers for REXUS, please use the provided gazebo simulating environment. You will be able to verify that your controller does in fact work the way you intended to, and this will serve as a check mark for us to be able to invite you into the physical facility to test it with the real live system.
We thank you for listening, and we hope that you will develop great projects for us to look forward to in the future.
Good day. My name is Jacques Verloon, and in light of the Petri program, I'd like to explain something about the use of the ESA Large Diameter Centrifuge, the LDC. I'm affiliated to the Free University Amsterdam Medical Center, and there I'm occupied with the craniofacial surgery department, working with 3D applications for patients' use, for patient, but also for cell biology. But most of my time I spent at ESA in Noordwijk, where I work on gravity-related research involving centrifuges, random positioning machines, microgravity simulation. And one of the projects in the future might be a very large centrifuge for people to live in. As a scientist, of course, you publish peer-reviewed papers, books, and in this case also do hardware development. These are the entities that makes it possible to pay my mortgage and to do research, so the funding agencies. Over the years, I've been involved in various flight opportunities. My first flight opportunities during my PhD was the IML-1 International Microgravity Laboratory. We did some experiments in the Russian Soyuz flights, again, shuttle to Mir missions, ISS, this is the Dutch Delta mission, another ISS flight, and parabolic flights. Was also involved in, worked for some years at the Breathed Engineering, a company that is most famous for, let's say, microgravity research, for the development of the MSG, the microgravity science glove box, currently used a lot in ISS. But we also did development for biological containers, and the BioPack facility was one of the facilities I worked on at the time. Especially in spaceflight research, in every profession, but especially in spaceflight research, it's really, you do things together. So it's really up to colleagues all over the world, international, that it makes it possible to do the experiments we did over the years. So, although I'm presenting, it's the work of many others involved. So I am affiliated to the Life and Physical Sciences Instrumentation Laboratory, LIST Laboratory at ESA in Noordwijk. And here you see ESTEC, which really is on the border of the Netherlands with respect to the sea. Here you see the North Sea, the dunes here, and here we have ESTEC. If you zoom in a bit closer, you see here the center of gravity, of course, the small little dome you see here. That is where the LDC, the Large Diameter Centrifuge, is located. So this is the floor plan of the lab. This is the dome I showed you here again. But there are various other facilities within the lab. We have the Life Sciences Lab, the clean room facility, meeting room, small workbench, the wet analysis lab, the support laboratory, and of course the gravity preparation lab, and the other lab where we do work related to Melissa, the life support system, and the C2 Research and Utilization, the FFC facility, since about a year. Here you see some images of the various locations. This is the main lab where we have incubators, flow benches, centrifuges, workbenches, and so on. So general purpose laboratory, a meeting room, where we can meet and present and discuss if needed, a wet lab with balances, the LCMS, some furnaces, other incubators, and so on. Support lab, -80 freezers, chemical cabinet, fume hoods, different waters, milieu and demi-water, autoclaves for sterilization of your work, glassware, and so on. A small workshop where we can do small modifications to the hardware if needed. If more modifications are needed, there is a bigger workshop at the ESTEC site, so you can do adaptations if needed. Of course, the LDC control room, where you see here the LDC at the back, but we have the computer used by the scientists or the user group, where you can command and monitor your experiment. This system is used by the centrifuge itself to operate it and to keep it under control. And then, of course, the preparation lab, where you can start working on your experiment in preparation of the actual implementation of the experiment in the LDC. Well, this is the LDC. Of course, with the LDC, you can increase gravity, but you can make more use of gravity in different moduli, let's say. First of all, you can, of course, expose your sample to various G levels, whatever the G level is. For the LDC, it goes up to 20. But you can expose your sample to different G levels, and you can extrapolate that data towards a lower G level. That is called, the principle is called based on the gravity continuum. And then you can explore what might happen on the low G level, although you work at a higher G level. So this is really a modeling sort of approach. Another way to make use of centrifuges, to say something about microgravity, although it seems a bit strange, but you can. This is based on the reduced gravity paradigm, where, if you look at the upper panel here, this is a regular microgravity experiment where you are on Earth at 1G, you're launched, and then you are at microgravity conditions, and your system, your sample is adapting, while under these microgravity conditions after the launch. What you can do in the reduced gravity paradigm is that you have your sample adapted to a higher G level, let's say 3G. You have a steady state at this 3G level, and then you lower your G level to 2 or 1G. And again, your sample will adapt to this lower G level. And the paradigm here is that the effects you would see here are similar to the effects you see there. Not the same, maybe not in magnitude, and not all the processes will be the same, but they go in the same direction. So you can learn a lot. Making use of centrifuges, you can learn a lot what might happen if you go to microgravity conditions. These are the main properties of the LDC. At full swing out, it's an 8-meter diameter system. It has 4 arms. It has various G locations, so you can move the gondola over one arm. We have 7 gondolas, although 6 rotating and 1 in the center. And the one in the center is really when you do animal-related work, and then there's a vestibular system involved to separate the effects of rotation and gravity. Centrifuges are great. The big disadvantage is that they rotate. Rotation is an artifact, and you need to control for that in some experiments. Not all of them, but in some experiments you want to do that. It's a swing-out system, which means that the gravity vector is always perpendicular to the floor of the gondola. It adapts while increasing the G's. It has a maximum payload capacity of 80 kilograms. The maximum G load is 20 G, fully loaded. The runtime is from minute to months. I mean, we can really run the system for several months without stopping. There's a 22 kilowatt motor in there to run it. And for those who want to do human-rated work, this centrifuge is not human-rated. Within each gondola, there are various facilities that can be used by the users. We have analog, digital, and PUE channels for video, RS-232 serial channels, Ethernet channels, USB 3 channels, of course power, 226 amps. We have the possibility to fix your sample to either to the floor, to the sides, or to the ceiling of the gondola if needed. Then there is a possibility for water and gas supply to the sample. I'm not going to explain this image. You can also look it up in the LDC user manual, where you see the systems on the rotating part of the LDC and the systems, computer systems mainly, on the static part of the LDC and the communication lines you have between the various systems. So if you're going to make use of data and communication within the LDC, most of the times we use remote PC as a way to communicate. If you want to do that and you have your own computer within the system, be sure that you have administrator rights to configure that system because it needs to be adapted to the LDC environment. And of course, sometimes we can use TeamViewer. And for experiment dedicated experiments, we need to really be able to fully address the system. Swing out, as I explained to you before, it's a swing out system. So the faster you rotate, the more the gondola will swing out to be more horizontal, never completely horizontal. The G factor is the resultant G factor is always perpendicular to the floor. If you want to make a piece of hardware and want to fit it in the gondola, please be sure that you take care of the round edges of the door of the gondola and the hinges you have. So it's good, I mean, again, you find the dimensions in the user manual, but it's good to leave some room to easily integrate and retract your experiment in the gondola. But also later on, if you want to manipulate the experiment while in the gondola, that you leave some room. This is an example of, the fastest start up and slow down of the centrifuge. Here you are at 1G and here is 20G. It takes about 60 seconds to come to full speed, and it takes about the same time, a bit less, 55 seconds to go from 20G to 1G. And then you can, you can provide any profile to the centrifuge, what is needed for your experiment. This is an example. We had a Soyuz launch. It takes about 8.5 minutes with various, depending on the stages of the rocket launch, you have various increases in acceleration during the profile. If you do an experiment, be sure that although we have an 8-meter diameter centrifuge, which is pretty large, there's always a gravity gradient. There is a gravity gradient going to the sides of the gondola, but also in height of the gondola. The best use of the LDC is to have an experiment really in the middle of the floor of the gondola. Of course, you always have hardware and structures in between, so it must most of the time be a bit higher. But be sure to keep your sample in the middle of the gondola. Otherwise, you have these gradients of inertial shear force over the sample, and there's an artifact you want to avoid. Again, you find references if needed. Some examples of in situ research utilization or planetary studies that we did in the LDC over the years. Here we have an experiment called IMPACT, where we had actually a fast projectile shot onto a surface, a regolith-related surface, to study the impact of this structure on this regolith surface. You can do studies related to habitats, for instance, because hypergravity has a scaling effect. So it scales with length, 1 divided by n in length. It scales with time, 1 divided by n square, and mass 1 divided by n cube. So you can make use of that, again, as I explained earlier, to extrapolate the data if you want to say something or what might happen on Mars or what might happen on the Moon. Another experiment here was with the ultrasonic drill that was from the University of Glasgow, where they want to understand the function of the drill at different G levels, how much power it would consume, how efficient it was. So they made a model of their system, and this is what they made here, the dashed lines here. There's a model of the drill at different G levels, and this was the actual test they did in the centrifuge. You see that they really have to adapt their model, depending on the results they had with the centrifuge. And again, this is done at higher G levels, but then you can extrapolate, what might happen when this drill is used on celestial bodies with lower than 1 G. Experiment accommodations. You have various ways to accommodate your experiment. As I explained earlier, you can have several G levels on one arm. So this means you can have one run where you have, for instance, 20 G and the other one 10 G. It's about a factor 2. You can run at the same time. We can have different temperatures in the gondola, so incubators, 37 degrees, for instance, for lots of biological, mammalian biological work. We can use multiple gondolas if you have the sample sitting in one gondola, but you need so much additional equipment that is not fitting in one gondola. You can use an adjacent gondola to accommodate the other instruments, and you can connect these two. And then there's also the possibility to prepare your experiment in the preparation lab before going into the LDC itself. So some experiment configurations. Here you have the impact experiment I explained to you earlier. Here we have a crab, maybe difficult to see, but there's a crab sitting in the center where we looked at the neurovestibular effects of higher G. Mass and heat transfer, where we had quite some cooling capacity, so liquid water capacities in there, which we ran through the experiment while at higher Gs. Planetary and glacier simulations. Here we have some model glacier material, which we exposed to different G level to again say something of what might happen with such systems on other planets. A bubble generation experiment where we used quite some cameras to to visualize and to monitor this experiment. Also used later for analysis. This is an experiment we did with zebrafish at higher G levels, and a similar experiment we did in a random positioning machine in a Kleinerstadt mode here, where we looked at the development of these fish, during the first 4 or 5 days. And finally, we have a possibility to use microscopes in the centrifuge. We have the EVOS system, the EVOS M7000, but also an in-house developed light sheet microscope together with the group of Stelzer in Frankfurt. And this is finally an example of a bubble experiment we did with the University of Barcelona. We also have in the lab, besides the LDC, we have the random positioning machine, which is a way to simulate microgravity. Gravity is a force, which means it has a direction and a magnitude. If you want to play around with the force, you can either play around with the magnitude or the direction or both. And this is what you do with an RPM. You constantly changing the direction of the gravity vector with respect to the sample. So this is this random rotation, so you generate a simulated microgravity. What we did with the big one here in the center is on top of this microgravity simulation, we put a centrifuge, and we can run the centrifuge at any G level we want, up to 2 G. So you can generate Moon G or Mars G or 0.7 G or 0.2 G, whatever you like. And then your sample put on there, and then you have this generated partial gravity lab. You can do the same here with this RPM. You don't see it, but this runs a different algorithm that also by software generates not a random rotation, but a sort of skewed rotation. So you also have a preference, for, let's say, Mars G or Moon G. So that's a software sort of simulation of partial gravity. And this is a regular RPM where you, again, simulate microgravity. So for the partial and hypergravity setup we have in the lab at ESTEC, you can go for simulated microgravity to partial gravity, hardware-related partial gravity, and then hypergravity, making use of the LDC. Before the campaign, preparation is key. So really be prepared when you come to do the experiment in the LDC. Think about the G-loads, the simulation, computers, fans, valves, every component you have within the system, whether it's capable of withstanding the loads you want to use during the experiment. Try to automate as much as possible. It increases the science and decreases the time during your stay at ESTEC. So we don't have to start and stop the centrifuge all the time. Test and try the experiment setup in your own lab. Perform complete test runs before coming to ESTEC. Don't have the first time, put everything together while being in the LDC. Really have to do all the tests at home. And for the lab use, if you do biology or mostly life science experiment, please bring your own disposables and any items you would need. Provide the experimental setup and protocols. You get lab forms for that as well. Think about the mechanical part, the electrical part, operations, how to access and handle your experiment while in the centrifuge, and the safety aspects are important. And we need these lab forms about 4 to 5 weeks before the experiment. The sooner the better, because then we can identify the things we still needed. Operation and logistics. Be sure how to handle your hardware when in the gondola, that you still have access with your hands or otherwise to modulate it if needed. Arrange your own shipment, very important, before and after the campaign, especially with experiments coming from the UK. Since Brexit, it's more difficult to ship items to and from the UK, so be aware of that. Bring sufficient data and data volume, when coming to the LDC, especially if you use digital video, huge amount of data. If you want to take it home, then please bring enough storage place. And for the computers I mentioned earlier, be sure to use administrator rights to do that. And normally we have working hours from some 9 to 1700 hours, so try to be within that time. Again, I'm not going in details to this page, but here you see all the experiments that were published in peer-reviewed papers. These are all DOIs you can go to and download these papers from all the work we did, all the peer-reviewed work we did with the Centrifuge. Any other questions or remarks? Don't wait. I mean, you see the email addresses for myself and my colleague running the lab as well, Alan Dowson. And here you have the URLs for the various facilities and other websites that might be of importance in gravity-related research. So with that, thank you, and don't forget to have fun.
Hi, I'm RInalducci. I'm working at the European Space Agency Research and Technology Center in Noordwijk, the Netherlands. On behalf of Space Rider project team, I'm going to give you a short overview of the European first reusable space transportation system, which is currently under development and expected to fly by the end of next year. The Space Rider program objective is to define and develop an affordable European reusable space transportation system, capable to perform experimentation and demonstration of multiple application missions in low Earth orbit. The system shall be able to implement a commercially viable business case and demonstrate to be self-sustainable in the long-term perspective. Space Rider is built on two main technology pillars: the successful intermediate experimental vehicle, IXV, flown on Vega flight number 4 in 2015, and Vega C, a evolution of Vega launch system. The primary goal of the IXV project was the development of a re-entry demonstrator to improve the European competencies in the field of atmospheric re-entry. IXV was launched from Kourou, the European spaceport, reaching a 400 km apogee with a suborbital arc, and re-entering over the Pacific Ocean, where it was successfully recovered. The heritage of IXV, its consolidated and validated technologies, and the acquired experience in the field of re-entry vehicles is fully reflected in Space Rider re-entry module design. Aerodynamic shape, thermal protection, thermal control systems, part of the avionics, GNC algorithms and software, structures, materials, propulsion system, ground control facilities, all are among the commonalities with this IXV precursor. Space Rider development and qualification phase is now ongoing and will end with the maiden flight at the end of 2024. Space Rider is made of two main modules. The re-entry module is complemented by an orbital service module, the so-called AVOM orbital module, AOM. Derived from the Vega C4 stage, it has been upgraded with a life extension kit called ALEC, which allows to operate for 2 months in low Earth orbit. The AOM will provide support to the re-entry module with attitude and orbital control, power, telemetry, telecom and data handling, and will ensure its separation at the end of the orbital phase. Space Rider's concept of operations relays on Vega C launch service. The pre-launch activities consist in the vehicle and payload assembly, integration and test to be carried out in Europe first, at the launch site and on the launch pad after the integration of Space Rider on Vega C launcher. The launch and ascent phase cover the nominal launch vehicle operation until the injection of Space Rider into orbit. The orbital flight phase starts with the commissioning and the preparation to initiate orbital and payload level activities. The payload's operation follows a mission timeline established on the ground, managed by the Payload Ground Control Center and the Vehicle Control Center. This period lasts 2 months and ends with the preparation for the orbiting phase. Upon the reconfiguration of Space Rider for the orbit and following authorization from the Mission Control Center, Space Rider performs the deorbit sequence, including a main engine braking boost, to achieve the desired condition for re-entry. After the boost, The re-entry module is separated from the orbital module, which performs a collision avoidance maneuver, leading to its destructive re-entry. After separation from the orbital module, the re-entry module performs autonomously the coasting, re-entry and descent, passing through hypersonic, supersonic and transonic flight regimes, till the triggering of a subsonic parachute deployment. At an altitude between 6 and 10 kilometers, a parafoil is deployed, allowing to perform a controlled glide till the landing site, where it reaches ground with proper touchdown conditions and landing accuracy. Upon landing, the vehicle is monitored, and a remotely guided mobile hangar enables the operators to approach it to perform the necessary safety operations. The early retrieval payloads are removed and handed over to the customer for processing at dedicated landing site facilities. The re-entry module is then moved to another facility for passivation and decontamination of the thrusters, final payload retrieval and preparation for shipment to the refurbishment facilities. In the post-flight phase, analyses are performed to identify any non-nominal behavior and needs for refurbishment. The re-entry module undergoes detailed inspections of all subsystems and equipment, and the necessary maintenance activities are performed. The re-entry module is then ready for acceptance for the next flight, with a new AOM within 6 months. The main additional feature of Space Rider re-entry module with respect to IXV is the 1200 liters cargo bay that can accommodate up to 600 kilos of payload in 8 different compartments, the so-called virtual lockers. Space Rider enables users access to and return from low Earth orbits for a number of applications such as microgravity experimentation, in-orbit demonstration and validation, Earth and space observation, telecommunication, educational mission, and any other commercial services requiring access and return from space. The flexibility of the main payload cargo bay allows to accommodate payloads with different sizes and needs, including pressurized and environmentally controlled facilities. Payload thermal control capability is provided by the large radiator mounted on the inner side of the cargo bay door that helps keeping the temperature of the payload mounting plates within 15 and 14 degrees Celsius, ensuring a plus or minus 5 degrees thermal stability and allowing to dissipate the excess power. Power supply lines from 30 to 400 watts are also offered to the payloads, with a maximum of 600 watts total, whose repartition among the various payloads is planned during the mission preparation phase. Payload data, including videos, can be handled and stored by the onboard data handling lines, adopting the most common transfer protocols. The onboard dynamic environment is defined and guaranteed to fulfill the experiment's needs. Microgravity levels down to 5×10⁻⁶ G can be achieved, as well as an accurate pointing towards the Earth or space. Stored data from the experiment are transmitted to the ground during the passage over the telemetry network stations. In these periods, telecommands can also be sent from ground to payloads for the proper execution of the experiments, even though not in real time. High-level security standard in the data processing and dissemination will be also guaranteed. Late access and early retrieval compartments are available for the installation and removal of sensitive experiment, as for instance, biological samples. Now, what is the way an experiment is selected and prepared to fly with Space Rider? The Space Rider payload embarked into the multi-purpose cargo bay is addressed as the payload aggregate, being, in fact, a set of multiple payloads and experiments coming from different entities having different characteristics and mission needs. The flight preparation is therefore a complex process that is carried out in various phases and by all the entities belonging to the Space Rider organization. One of its key elements is the standardization of the process, to simplify the efforts of definition and management of the payload aggregate. Under ESA coordination, acting as a Space Rider system operator, the design of the payload aggregate is responsibility of Space Rider industry primes, namely Thales Alenia Space Italy for the re-entry module, Avio for the orbital module, Telespazio and Altec for the operation. Contributions are also requested by the Launch Range Safety Authority, the CFG, and the launch operator, Arianespace. The final scope of this activity is to guarantee compliance with the vehicle capabilities and to harmonize the needs of all payloads in the aggregate. Key factor is the interaction with the experiment providers and with payload sub-aggregators, if present, who act as intermediate collectors and integrators of multiple experiments within a single flying facility, for example, more biological experiment into a single laboratory. The payload aggregate preparation process from payload selection to post-flight retrieval is subdivided in different phases. A preliminary phase 0 involves a screening and assessment of potential payload candidates based on the compatibility of the payload's declared interface with space rider accommodation capabilities and mission characteristics. Selected payloads are then invited to submit more detailed information in the form of an interface requirement document and a safety file to advance to the next phase. Phase 1 regards the preliminary accommodation studies in the cargo bay based on the information provided by the payload's IRD and safety file. Payload accommodation in this phase main considers mechanical, thermal, power and data handling constraints. Several aggregate configurations are elaborated which optimize customer needs and vehicle service capability. A regular interface meeting with payload customers guarantee the availability of updated information at each stage of the payload design and development process. Phase 2 introduces the contribution of the SRS Industry Prime Aggregate Design Authority to first assess the feasibility of the preliminary configuration studied, allowing the signature of a memorandum of understanding with the payload customers. Based on payload's consolidated data, the preliminary mission analysis is performed. The objective is to evaluate and confirm a suitable preliminary payload aggregate that is harmonized and compatible with the vehicle capability and mission timeline. The successful conclusion of the PMA leads to the signature of a flight service agreement with the payload customer. Phase 3 deals with the execution of the final mission analysis based on further consolidated payload data to confirm the final payload's aggregate design. This phase includes the missionization of the vehicle to the needs of the defined payload aggregate, including hardware, software, and procedural adaptation when needed, ground and flight operation plans definition. Phase 4 consists in the flight preparation with the integration of the payload's aggregate into the vehicle and the final verification. Phase 5 is the actual flight, while Phase 6 deals with post-landing operation when payloads are disembarked and handed back to the customer. The standardized payload aggregate preparation process has been conceived to optimize efforts and allow reasonable lead time for customer follow-up and mission preparation, in coherence with a project target launch rate of 2 flights per year. The design of Space Rider first mission is currently ongoing. Alternative payload aggregates have been proposed according to the customer portfolio achieved to date, with some aggregate options that are shown here. All the principal information included in this presentation, as well as further details on Space Rider and the multipurpose cargo bay features and services, are reported in the user guide for the Space Rider reusable free flyer platform. This document is currently under revision and will be updated upon completion of Space Rider critical design review process within the end of 2023. The applicable issue is made available upon request to Space Rider users, experiment owners, and sub-aggregators. Thank you for your attention and see you soon on board of Space Rider.
Hello everyone, so my name is Armelle and now we will be talking about BEXUS. BEXUS stands for Balloon Experiments for University Students. BEXUS is part of the REXUS BEXUS program, and program is a bilateral agreement between 2 agencies, SNSA, Swedish Space Agency, and DLR, the German Space Agency. We also are working with ESA, European Space Agency, make the call for proposal open to all universities from ESA member states and associated member states. In this program, you can also find 3 other partners, Moraba, our colleagues from the rocket mobile bases in Germany, ZARM, the Center for Research Under Microgravity, and SSC. So, a bit about myself. My background is space engineering. I got a diploma from a French engineering school called ESTACA, and then a specialization is system engineering. After my graduation, I got the great chance to join the European Space Agency as a young graduate trainee, where I discovered the great program of REXUS BEXUS. So a couple of years ago, I had the great chance to join SSC to take care of REXUS BEXUS, but from Sweden this time. So what is SSC? SSC stands for Swedish Space Corporation, and actually you can find us a bit everywhere thanks to our big network of ground stations. But today we're talking about BEXUS, so I can more focus on the science and launch services. SSC is developing experiments, like actually the students are developing experiments on BEXUS. And we are also developing flight systems for rockets, but also for balloons. and we are launching them. So you can also find us at ESA Space Center, and if you are part of BEXUS, you can actually come to ESA to launch your own experiment. So since the 60s, we have been launching sounding rockets, stratospheric balloons, but also technological demonstrator. And more recently, we had opened our activity to orbital launchers. So now we can go more to our topic of BEXUS. BEXUS is a stratospheric balloon. So what is that? Stratospheric balloon, it's a balloon that lifts off a gondola payload to the stratosphere, so between 25 to 40 kilometers. That's dependent on the mission. We can do many missions with a stratospheric balloon. We can do transatlantic flights, for example. We can go around the pole, North, South Pole as well. But we can also use the stratospheric balloon for drop test. We can have missions for like a couple of hours up to a couple of weeks. Of course, depending on the winds and on seasons during the year. So this is inside this context that you can find BEXUS. So what is BEXUS? On the top of BEXUS, you have the balloon. This is a plastic envelope, and we are filling it with helium. Below this, you have a couple of devices that enable to do the navigation and also to terminate the flight of the balloon. You can also find a parachute because we are recovering BEXUS. All of our payloads are recovered after the campaign. And then you have other devices, especially for the navigation, the localization system, and the transponder. Then I will go slowly to the Empire. This is a system from S-Range, and this is basically the one that pilots, let's say, the BEXUS. And underneath, your stuff, the experiments. We have this gondola, and on this gondola, which is an aluminum frame, this is where we found all our science. I will show you a little bit later on how you could accommodate your experiments. But on BEXUS, your experiment could be directly connected to a power supply and have access to communication, both telecommand and telemetry. In terms of typical mass breakdown, for 100 kilograms of payload, we can go to BEXUS for about 25 to 30 kilometers in the stratosphere. This is basically the graph we are using, and according to the season of the launch, we can check the altitude, also depending, of course, on the payload mass. So what about the mission phases? So this is a graph to explain a bit what's happened to BEXUS. Of course, first of all, we are launching. We go slowly into the troposphere and then stratosphere at about 5 meters per second. And then we arrive to the float phase. So the float phase is basically the maximum altitude we can reach, and we are staying for a couple of hours. Most of the time, this is where the science is basically happening. If we want to extend the floats, we can do it with opening a valve. Then we have a new float, so we can extend it. So we release some ballast, and then we just continue our launch. This is right now not standard for BEXUS, but this is absolutely possible to add it for a stratospheric balloons mission. And here you can see a nice picture that was taken from a team of us called Bob from the University of Cranfield. Nice pictures from the stratosphere. So this flight is beautiful, but then it's time to stop and to go. So we have to come down. This is the cut down. Interesting part for your experiment. That's a kind of a shock. But don't worry, after the free fall, we are opening parachutes and we slowly go down to the Earth again. So we talked a little bit about the environment. So it's time to think about what's happened to my experiment during flight. What about temperature? What about pressure? What about vibration? And of course, as I said just before, what about shocks? So indeed, the environment is not super nice, not always. So it's kind of dynamic. We have acceleration when we are releasing the balloon. Of course, we go up in the stratosphere. We have a rotation of the gondola under the balloon, and we have a shock at landing. So your experiment has to be robust to this environment. The interesting aspect, of course, of BEXUS is also the temperature environment. When we go to the stratosphere, it's kind of cold. And actually, you can expect some minus 50 degrees Celsius in the stratosphere. However, the stratosphere is not the only thermal environment important. You have also to think about the ground. We are launching from S-Range, and S-Range is above the Arctic Circle. Can be cold. So the ground operation is also important to consider. So this is, for example, an example of our atmospheric model showing basically the evolution of the temperature according to altitude. Second thing, pressure. We are in stratosphere. Pressure is low. It means like your experiment also has to be robust to vacuum. In general, we are between 10 to 20 millibar, and we are always recommending our students and the experiments to make testing. Now about the launch campaign. When all the design is done, building is done, and test is done, then you are invited to the campaign. So then all the teams are invited to ESA Space Center in the Swedish Lapland, where we have 10 days together to make it happen. So the students are coming to us and we have different test and preparation activities that I will show you. We are actually gathering in the dorm. That's one of the biggest buildings we have for integration. And we are launching on the balloon pad. So that's the one you can see on the picture with a lot of snow on it. And why a lot of snow? Because actually we are launching usually in October. And yes, we might have snow in Lapland at that time. So what's happened to your experiments? Of course, the first days are dedicated to the preparation and individual experiment tests. So you can see the students preparing experiments, mounting them on the gondola, and start the testing with the flight system. When everyone is ready, everyone is on the gondola, then it's time to make the test all together, and that's the picture you see here, the integrated gondola with all experiments. And after that, the compatibility with the system from SSC as well. When it's done, eventually, we launch. So of course, on one side the experiment on the balloon, and you as a student being the experimenter at the ground stations. So that's your ice basically for the whole duration of the mission. That could be a couple of hours. Regarding your payload now, if you're interested, where can you put your payload? But what can you do on BEXUS? Actually, BEXUS is open for a wide spectrum of science, from atmospheric physics, fluid physics, but also radiation physics, material science. We also had biologists on the BEXUS. And I say that this is not an exhaustive list. It can always be open to new science, even also for technology demonstration. So here, for example, you see that we have 2 BEXUS that we are launching per year during the same campaign. And this is how we are splitting the experiments on the gondola according to what do you need. We are putting the experiments that are compatible with each other on the same gondola. We can have up to 10 experiments per campaign, so we are trying to split between those gondola, usually between 4 and 6 experiments per gondola. So where can you put your experiments? Well, most of the time on the floor. That's the most comfortable way for your experiments to sit on this gondola. It's a very standard interface. Nevertheless, you might need to have access to the outside environment. Then you can be on the top, having clamping system that you are developing. Maybe you want to be on the side of the gondola with a boom. That's also possible with a clamping system again. Or maybe you want to be underneath. So this is only possible if you are like very light, but it's possible as well. Then we are covering the gondola with these white curtains, and this is mainly to protect it from sun radiations. That's us that doing this for the experiment. If you want to have access to the outside, we can always fold a little bit the curtains so you can have access, of course. Finally, what is important for you to know is like we will provide you a power supply. So you will basically have a battery dedicated to your experiments, and you will have access to what we call the E-Link, which is our telecommunication system. So you will just be connected to it. Finally, the tips. I hope you have been interested and that you will want to join BEXUS. But little things to know before application. First of all, we have a BEXUS user manual. This is available on the website. So please have a look carefully in our user manual. That's a lot of information, very important for you on it. So you have to read it. Then focus on the primary objective. We don't need to have application with like thousands of fantastic objectives. No, please be focused on one objective, focus on it, and present it. That's the most important. You can also have a look on our website about the history of experiment that has been done on BEXUS in the past, if it can give you some ideas. Of course, we want to know why you want to fly on BEXUS and not to another vehicle. So also work a bit on the justification on the vehicle. Finally, if you want to have help before you apply, or if you have questions, never hesitate to contact us. We are always here. Again, on our website, you found a page with our contact information. Do not hesitate to ask questions. And obviously, don't be scared. Just try to join us. Thank you very much. And if you want to have more information, again, our website is a very good point of information for you. And you can also follow us in a more regular basis on our social media. Thank you very much. Hello, everyone. On this video, I will explain you a bit about REXUS, our rocket experiments for university students. So I'm Armelle, and I'm part of the REXUS BEXUS program. REXUS BEXUS program is a bilateral agreement between 2 space agencies, the National Space Agency from Sweden, SNSA, and the German Space Agency, DLR. We also have collaboration with European Space Agency that's made the call for proposal open to any university from ESA member states and associated member states. We have 3 other partners on this program, Moraba, our colleagues from the Mobile Rocket Bases in Germany, ZARM, the Center for Research in the Microgravity in Bremen, and SSC, the Swedish Space Corporation. So my name is Armelle, and my background is space engineering. I have a diploma from a French engineering school called ESTA and specialization in system engineering from Suter. I get the chance to be a YGT, a young graduate trainee at ESA a couple of years ago, and this is where I discovered REXUS BEXUS. So a couple of years later, when I had the opportunity to come back to the program to take care of it as a program manager at SSC, of course, I joined with pleasure. A little bit of words about SSC. What are we doing? One of our first activities, like you can find us a bit everywhere in the world because we have a worldwide network for ground stations for the satellites. But today we're more focused on the science and launch services because we are developing experiments for sounding rockets, a bit like our students are doing on REXUS, developing their experiment for this sounding rocket. We are also developing services and flight systems for sounding rockets, stratospheric balloons, and we are, of course, launching them. For that, we have to go to Esrange Space Center. The Space Center is above the Arctic Circle in the Swedish Lapland. We started in the 60s to launch sounding rockets. We are also launching their stratospheric balloon, but also a technology demonstration, a project. And more recently, we had test facilities for propulsion and now orbital launches. So a few words about sounding rockets, because REXUS is about this. It's a sounding rocket. So what is this kind of vehicle? Sounding rocket, it's an activity that really blossomed in the 60s, mostly because of interest in atmospheric research, but also in the interest of the northern lights, also called auroras. Sounding rockets, it's a vehicle that can enable you to go to 45 kilometers, but also to more than 1,000 kilometers. So it's a very wide spectrum of science and experiments you can do on such vehicles. It can be used, for example, at the moment for microgravity research as a platform for that. But we can still conduct atmospheric research and also biology. This is just an example because actually the list is not exhaustive and we have a lot of different science that are using such vehicles. Same for technology demonstration. You can use a sounding rocket, for example, to qualify a new system for re-entry, for navigation. You can also do material science. And again, the list is not exhaustive. So now we have to talk about REXUS because we are part of the sounding rockets family. REXUS is a vehicle composed by a single stage motor. This motor is called Improved Orion and it's solid propulsion. It offers 26 seconds of propulsion phase. You can also see 3 fins on the rockets that enable us to stabilize the rocket. On the top of the motor, you will find motor adapter and what we call the yo-yo despin. Why we have a yo-yo despin is because of stabilization, we have a rotation around the longitudinal axis of REXUS. When we want to stop the rotation, especially to enjoy the reduced gravity phase of the rocket, then we are opening this yo-yo, which is a cable with mass at the end of the cable, to stop the rotation. So we pass from 4 Hz to 0.08 Hz. On the top of that, you will find a recovery module. The recovery module is developed by our colleagues from DLR Moraba, and they are opening drop parachute and main parachute, because of course we are recovering the whole payload of REXUS. On the top, you will find the service module. The service module is providing the power supply to the experiment and also a system for communication. If your experiments need to charge a battery, for example, you have a charging line available. Maybe you want to have a live stream during the flight, then you can use the TV channel. And if you have any system you would like to eject during the flight, you can also use the power line that are available. This is always upon request. And then on the top of that, then you will find the experiments, the modules. So it's like one module is one experiment. And we have a couple of them on REXUS, up to 6 actually. The different heights of the module is according to the needs of the experiments. We can go to like a very small module of 120 millimeter heights, but we go to like 330 millimeter, for example. It depends on what you need. A module can be very just easy, like the outer structure that we are providing, and you're putting your experiment inside. But maybe you have like outer things that you want to put outside of the module, such like antenna. This is possible. Or maybe you want to eject something from the module. That's the picture you see at the bottom. That's also possible. And of course, we have a special place on the rockets. It's the experiment that is located underneath the nose cone. So this is also possible to be here. And we can open the nose cone during the flight. Then the experiment has an exposition directly to the outside environment. We usually have only one experiment there, but it can also happen that we have a tiny experiment that could be mounted even on the top of the first one. This is not standard, but that can happen. You will also find there the tip of the nose cone with our GPS antenna. In terms of mass breakdown, so you can see here the different mass we have for the REXUS and especially for the payload. Of course, we have estimation during the whole design phase. And then we go for what we call the spin and balance test campaign. And we go for that at S-range. This enables us to have not this time estimation, but real measurements of our mass. Then we can predict our apogee and our flight parameters. So for REXUS, usually our apogee is between 70 and 90 kilometers according to the payload mass. Depends on our students and experiments. So what about the mission phase? Of course, we start with the liftoff. We have the ascending phase with the propulsion. After 26 seconds, we have the release of the yo-yo despin, the motor separation. We are separating the nose cone if for this flight we want to eject it. And then this is where we are starting the reduced gravity phase. We reach the apogee, and then we go to the period of freefall. After a period of freefall, we are opening the parachutes and we have a more gentle descent until we go to the impact. We always come back to Earth. What about flight environments? So we are talking about rockets, so we think a bit about temperature, of course about pressure, but a lot about vibrations and about shock. Because again, being an experiment on a REXUS rocket, it's not like going on holidays. So what happened to it? Very dynamic environments. We have big acceleration, mainly during the propulsion phase. We can have about 20 G because of the motor. We have a rotation, it's spinning, a lot of vibration, and we of course have an impact when we are opening parachute and when we are impacting the ground. Thermal is also something to think about. During the launch, of course, we have a raise of temperature because of course, the velocity of the rocket inside the atmosphere. But actually, what usually the students don't think about is the environment on ground, because this is the one that is a bit more tricky. We are launching from S-range. It's cold. At some point, the rocket will be outside waiting to be launched. And if you have an experiment, especially with liquid inside, then this phase is mostly the most important for you to consider because it can be cold. Of course, pressure environments think that we are going quite high in altitude. So we are reaching vacuum level of about 0.5 millibar, meaning that we have to think about pressure vessel, maybe corona effects for your electronics. That's all the things that have to be tested for REXUS. Finally, about the launch campaign. So when you finish the design phase, you have manufactured and then tested your experiment, then you are invited to the Space Center of S-range to launch. We are usually launching in March. It's during 12 days and all the REXUS teams are coming together. We are having several days of preparation and testing in usually the building that we call the Dome. And then we are launching from what we call the MRL, the multi-rocket launcher. That's the yellow ramp you see on the picture. So the first days are dedicated to preparation. So the teams have their own working area where they are preparing their experiment, or let's more like finalizing. Never think for the first time during campaign. It's really finalization, preparation to flight. When all experiments are ready, then we can put them together on the bench and make integrated check. So test all together. The payload is fully assembled and our students are next to their ground station. That's where you can see them on the picture with their computers. And when it's fine, well, it's time to launch if the weather is nice with us. So this is what can happen. This is a video from REXUS 27 that we launched in November 2022. And actually, you could see at the beginning of the video that there is a foam. We wrapped up the payload. This is an insulation because it's cold. So that's why we have this insulation foam on the payload. So what about the payload? If you are interested, what can you do? Again, in terms of ideas, this is very open. I strongly recommend you to go to our website and see the history of experiments that already flew on REXUS, because we can do scientific investigation, but we can also have technology development under REXUS. So both are well represented from our teams. Then you see here that we have 2 REXUS launch per year. They have the same campaign. So we are basically distributing the experiments between those REXUS according to their flight requirements. So we are ensuring that everyone is happy with their neighbors. We have up to 10 experiments for the campaign and up to 6 experiments per REXUS. Here you have the example of REXUS 30. We had the micromoon experiment under the nose cone. Nose cone was ejected. Then we had the B2 team, IMFEX and Aster on the same payload stack. As an experiment, you can accommodate it inside the module. So here you see 3 examples of how you can integrate your experiment with example of ECLIDA, RAPTEX or Aster experiment. So basically safely, comfortably inside the module. We are providing the module to the experiments, but the students are responsible to produce all the rest of their experiments. If you're under the nose cone, then this is how the experiment can look like. You see that in both teams here, Spear and Daedalus, they're basically trying to use like the whole available volume they have for their experiments. So you can see Spear on the first picture, which was supersonic parachute system development, and also the Daedalus space seeds that we launched respectively in November 2022 and March 2023. We are also providing the power supply coming from service module, and the interface is a standard D-sub connector. You also have access to communication via the same interface. Then you have, of course, the telemetry via our service module, and you can also receive signals from the service module. So we are calling them SOE, SODS, and the liftoff. It's respectively stand for like the start of the experiment and the data storage of experiment, but actually you can use those signals however you want, except the liftoff, of course, that is common for all our experiments. As said, if you want to have access to a TV channel, it's possible, and then you have live stream, then you can collect the video after the launch. Some tips, and this is the final recommendation for you. Please, if you want to apply, the first thing to do is to go on our website, look at our REXUS user manual. There you find all information you need, especially the interfaces, the program constraints, but also the vehicle specifications. Second thing, please define your experiment objective. It's better to focus on one objective than having like a couple of objectives and basically going a bit everywhere. We want to see an experiment that have a focused objective. Again, you can have a look at what has been done in the past to get some inspiration and to know what's feasible on REXUS BEXUS. Please justify clearly why you want to fly on REXUS. It's fun to be on REXUS, but why REXUS is a good platform for your experiment. That's important for us to understand why you want to be with us. And of course, please don't hesitate to contact us. If you have any questions about the user manual, any questions about the program, the vehicle, you can find our contact on the website. There is a page dedicated to the contact of REXUS BEXUS. Never hesitate to contact us before the application. And finally, just don't be scared. The program is made for students, it's made for people, it's here to learn. So just try if you really want to join us. Thank you for your attention. And if you want to have more information, please don't forget our website, and you can follow us more regularly on our social media.